Good day, everyone. This is a catch-up lecture on digital computer technology. In this course, we will cover basic organization of computers, machine representation of instruction and data, code conversion. We'll talk about the binary coded decimal, gray code, SS3 codes, then Boolean algebra, and the minimization techniques, such as the Karnaugh maps, the McCloskey minimization technique, or that's the tabular method. And then we'll also look at sequence and data flow control, error detection, and correction techniques. To begin, we want to consider the simple evolution of the microprocessor, which is the heart of the computing device. And here we get to see that it all started with logic gates. So logic gates are combined into more complicated units called adders and memories. Okay? So here, logic gates, which are combined. And then we now see that these gates put together to be a microprocessor. The microprocessor itself, microprocessor, runs assembly programs. Okay? So the microprocessor itself is a digital system that executes machine language instructions. Okay, so the microprocessor is a digital system executes machine language. So in the digital design, so I want to talk about digital design. Digital design. Two things come to mind, which happen to be most important metrics of interest. That is speed and energy. So we want to design high-speed systems. And we also want to design lower energy consumption systems. And for us to achieve high speed, then we want to minimize the propagation delay. Okay, so we want to see how much we could design the system with minimal or with limited or small amount of gate devices, or better still, improved technology. So hence, a microprocessor is an integrated circuit where data processing, logic, and control are included. So it contains both the combinational and sequential circuits. Okay, so combinational and also sequential circuits. Right? So as we'll see in this series, the earliest design made use of transistor logic design, transistor logic, that is TTL, while the most recent or earliest systems use series, right? So in order to relate with the system of design, I think it would be of interest to break down the complex system into smaller modules. And that will bring us into the abstraction of the digital computing system. And we know that abstraction is a critical technique for managing complexity. So in terms of dealing with this level of abstraction, so coming from the highest level of abstraction, we have the application software. And here we have the programs running. And just below it, we have the operating system. We have device drivers and controllers. All this, we have the architecture. We have instructions, registers. All this, we have the micro architecture. We have data cards, controllers, just below this, we have the logic design. Here we have the others. Below this, we have the digital circuits. We have the AND gates, OR gates, NOT gates, inverter, then we have the NAND gates, etc. And below the digital circuit abstraction is the analog circuit. below the analog circuit is a devices, and then below this is the physical electronics. So for the analog, we have amplifiers, filters, devices, we have transistors, diodes, and for the physical electronics, then we deal with electrons. So this is where we are particular about the motion of electrons. And then we have to solve the Schrodinger equation, which provides sufficient information for the design of transistor devices and other devices. And putting this together, we could develop some of our integrated circuits, like amplifiers, then we can design filters. And putting this together, we could design the switching devices, logic devices, the digital circuits, which when put together, we could design the ADAS memories all the way. Okay. So while at this level, we deal with quantum mechanics, lecture series on that, and Maxwell's equations. So for the devices, we talk about the electrons, the devices, the transistors and diodes put together, and all of that. Then the microarchitecture links the logic design and the architecture levels of abstraction. And it involves combining logic elements to execute the instructions defined by the architecture. By the architecture itself describes a computing device from a programmer's perspective. The operating system is pulls us from the hardware level, or RAM, to the software realm. And it handles low-level details such as accessing a hard drive and managing memories and the rest. While the application software uses the facilities provided by the operating system to solve problems for the users. So in terms of managing the complexities relative to system design, be it hardware or software, we get to deal with the three Y's, okay? Precedence. Hardware. Software. System. So the first of which is the hierarchy. And this involves dividing the system into modules, okay? Here we divide system. So the importance of dividing each of these modules until the pieces are easy to understand. Then the second Y, that's Y, Y is modularity. So in this case, it states that the modules have well-defined functions and interfaces. So we'll talk about each module having well-defined functions and interfaces. And this is such that they connect together easily without unanticipated side effects. So it means that there should be no side effects. The design of one module should not impede the function of another module, except it is so required. So for the third Y, we have regularity. And this 6 uniformity among the modules, okay? So common modules are reused many times, reducing the number of distinct modules that must be designed. So when it comes to digital abstraction, we represent information with discrete value variables. And it should be noted that variables are a finite number of distinct values. And the digital computer uses a binary representation in which a high voltage indicates 1. So voltage is 1. So we have to move. This is 1. And a low voltage indicates 0. So hence, the amount of information in a discrete value variable with n distinct states is measured in units of bits, and we deal with that in Shannon information theory and coding, where unit of information is the same as log n is 2 in bits because it is a base of 2. And much on this has been covered in the information theory series, and you may want to look up these videos. Now, a binary variable actually conveys log 2 is 2, which is equal to 1 bit of information. Now you'll observe that the word bit is short for binary digits, okay? Bit, same as binary digits. So the it here and the b here forms. Also know that an n digital decimal representation, decimal represents 1 of 10 to the power of n possibilities. That is an n digit decimal represents 10 to the power of n possibilities, right? That means we have 0, 1, 2, 3, 4, all the way to 10 to the power of n minus 1. And this is called the range of the number. This is called the range now for a 2-digit, for n equal to 2, that is a 2-digit decimal number. So we have 1 of 100 possibilities, right? That is 10 to the power of n, which is 10 to the power of 2, which is what I use. Such that we have 0 to 19. So we should know that in binary, column width from 2 to the power of 0, we have that to be 1. 2 to the power of 1, we have that to be 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. 2 to the power of 5 is 32. 2 to the power of 6, 2 to the power of 6, 64. And 2 to the power of 7 is 128. And 2 to the power of 8 is 256. 2 to the power of 9 is 512. 2 to the power of 10 is 1024. 2 to the power of 11 is 2048. 2 to the power of 12 is 11. 2 to the power of 12 is 4096. And 2 to the power of 13 is 8192. Then 2 to the power of 14 is 16384. And 2 to the power of 15 is 32768. And 2 to the power of 16 is 65536. Right? So an n big binary number represents one of 2 to the power of n possibilities. Okay? So if we have n, now here we have n digital decimal, this decimal, right? So when we have n big binary number, this represents 2 to the power of n possibilities, right? Such that we have 0, 1, 2, all the way to 2 to the power of n minus 1. So going like this, the decimal representation of the form 2, 2, 3, 4 base 10, for instance, is the same as 2 to the power of 10 plus 2 to the power of 10 plus 3 to the power of 10 plus 4 times 10 to the power of 0, 1, 2, 3, right? And while in binary, the binary representation of the form, say 1011 base 2 will be the same as 1 times 2 plus 0 times 2 plus 1 times 2 plus 1 times 2 to the power of 0 of 1 to the power of 2 to the power of 3, right? So this will give us 11 this time. So binary to decimal and decimal to binary conversion is pretty straightforward. So when we have 1011 1, 1 is 2, we know that this is equivalent to 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, right? And so the weight here is 1, weight here is 2, the weight here is 4, the weight here is 8. So in this case, 0 is not active. So we have this is also not active. So what we have here is 8 plus 2 plus 1, right? And that gives us this thing. Okay, and one will also have this 11, so 8, 4, 2, 1. So 8 plus 8 plus 8 plus 2 plus 1, that is 8 plus 2 plus 1 is equal to 11. So this is not active. So we have 1 here, this is turned off, this is turned on, this is turned on. So we get a binary. So it should be noted that in practical digital systems, electronic translators are used for converting from code to code. Okay? So you have electronic translators, right? You use them to convert from code to code, right? They are usually called encoders and decoders, okay? We call them encoders and decoders. And the types of binary codes are the weighted binary codes and then the non-weighted binary codes. Okay. So we'll just run through the code conversion as a way. So we have the binary coded decimal, the gray code, and the excess codes, right? Already established that that electronic translators are used to convert between those codes, and we call them encoders and decoders, right? And we have the types of binary codes. The weighted, binary code, and the non-weighted binary code. Okay. And for the weighted binary code, we have the binary coded decimal, which comes with the following weights: 8421 or 4221 or 5422. Then for the non-weighted binary codes, we have XS3 codes and the gray code. Now, the BCD codes are weighted because they have weights assigned to each binary digit. Okay? So it should be noted that while binary variables are used to represent information, logic gates are simple digital circuits that take one or more binary inputs and produce a binary output. So let us consider the binary coded decimal. BCD codes. Now, the BCD code makes conversion to decimal much easier. So this code is more precisely known as the 8421 code, right? Or that's the 8421 BCD. The 8421 gives the weight of each bit in the 4-bit code. So other examples were stated in the previous slide. So for BCD conversion, each decimal number is expressed as 4-bit BCD number. So let us say we want to express 212 decimal number as BCD. So it means that we take on looking at 8421. So this is the first bit. So 2, it means that this bit position is on. So we have 0 is turned off, 8 is turned off, 4 is turned off, 1 is turned on, 0 is turned off. Then for 1, 8 is turned off, 4 is turned off, 2 is turned off, only 1 is turned off. Then for 2, we have the same 0, 0, 1, 0. So 212 is the same as 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, and 0, 0, 1, 0. So it should be noted that the binary equivalent number is different from the BCD number. So let's say we want to express 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, on 0, 1, 0, 1, BCD. So it means that we have BCD. So let us separate them. 0, 0, 1, 0. And we have 0, 0, 0, 0, 1. 0, 0, 1, 0. 0, 1, 0. And decimal, this is the same as 2, 1, 2, 1. Now 4 and 1 are turned on, so 4 plus 1, that is 5. So if we say 212 divided by 2, that would be the same as 106, remember 0. And then 106 divided by 2 will be the same as 53, remember 0. Now 53 divided by 2 will give us 26, remember 1. Now 26 divided by 2 will give us 13, remember 0. So 13 divided by 2 will give us 6, remember 1. And 6 divided by 2 will give us 3, remember 0. And 3 divided by 2 will give us 1, remember 1. And 1 divided by 2 will give us 0, remember. So we also have 0.5. So 0.5 times 2 will give us 1, 0. And now 0.0 times 2 will give us 0.0. Okay. So now I want to take it from bottom up, right? So this string color. So let me take this bottom up, right? So here we have 1, 0, 0, 0. And this is 1. This is 2. So hence the BCD number, this BCD number is equivalent to this binary number. So BCD and the binary equivalent are different. Okay. So let us say we want to convert 1 0 0 0 1 0 1 0 1 0 1 binary to BCD. So we have the binary, which is 1 0 0 0 1 0 1 0 1 0. So we have to first convert to decimal, which is 1 2 3 4 5 6 7 8. So we call 1 2 4 8 16 32 64 128. 1 2 3 4 5 6 7 8. So these are the first 8 bits. So this is the same as 128. So it's the same as the bit position. 128 plus 0. This is turned off, this is turned off, and this is turned off. So that's like plus 0 plus 0 plus 0. And then this is turned on, so that's 8. It's 8 plus 4 is turned off. Then 2 is turned on, plus 2. Then 1 is turned off, plus 0. So plus. So this time this times 2, that will be 0 and 5 plus 0 plus 0.125 because that's times 2 to the power of minus 1 times 2 to the power of minus 2 times 2 to the power of minus 2, right? So all of this is so this is 0 times this, 1 times this, 1 times this. So that would be 1 over 2, 1 over 2 over 3. So that was 0.5 and 0.125. This is going to give us 138.625. And then from this, we will come back to BCD, right? So this now is the same as 1, that's 0001, 0001. Then 3, it means this 2 bits are turned on. 0011 for the 8421 BCD code, right? And then 8 we turn on. So use the first bit, that is 1000. Dot 6 is turned on, that's 4 plus 2, so that will be 0, 1, 1, 0, and then 2 is turned on. 2 is turned on, that's 0, 0, 1, 0, and then 5 is turned on, 4, and 0, 1, 0. So hence, for this binary representation, the BCD code is that 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 1, 0. BCD code is equivalent to 1, 0, 0, 0, 1, 0, 1, 0, 1, 0. So now let us look up the non-weighted binary, non-weighted binary codes. So we have the SS3, which is SS code, and the gray code, right? So in this type of codes, the gray, each bit does not have a special weight assigned to it like the BCD. So when we consider the SS3 code, it's a special type of BCD code, except that each 4 bits group in the SS3 code is the same as a specific decimal digit. And the SS3 number is always 3 more than the 8421 bits by a BCD code. So SS3 number is always 3 more than 8421 BCD. So in other words, the binary 0011, which is from the 8421, that's 3. 2 plus 1 is 3. It's always added to each 4 bits. Okay. So let us convert 82 decimal number. So SS3 number. So we have 82 plus 3, which gives us plus 3. Well, let's separate it, okay? Let's separate this for ease of understanding. So we have decimal, which is 8, 2. So we add 3 here, and we add 3 here. So this will give us 11, and then this will give us 5. So the SS3, which is a special BCD code, will now be for 11. Recall 842, 8421. So for 11, for us to get 11, it means 8 plus 2 is 10 plus 1. So that will be 1011. So it means this is turned on. Why for 5? 4 is turned on, 1 is turned on, 2 and 8 are turned off. So that will be 0, 1, 0. Okay. So for 82 decimal, we have 0, 1, 0, 1, 1, 0, 1, 0, 1. SS3. Now I want to convert 01000 00 BCD to SS3. So for the BCD, we have to bring into 4 bits. That's 0100 and then 0100, right? So we have to add 3, that's 0011, that's 3 plus 0011, we call 8421. So when these two bits are turned on and these are turned off, so that was 0011, that's equal to 3, right? So we'll add this plus this is 1, this plus this is 1, this plus this is 1, then 0. This plus this is 1, 1, 1, 0. So for the SS3 code, we have 0, 1, 1, 1, 0. Now, let's try to combine 1, 0, 0, 0, 1, 0, 0, 0, SS3 to decimal. So in SS3, we have 1, 0, 0, 0, 1, 0, 0, 0. So we have to walk backwards. So we're going to subtract, since we want to convert to decimal, so we'll have to subtract 3. So that will be 0, 0, 1, 1, so 0, 0, 1. All right. So this minus this is impossible. So we're going to borrow 1 here. It becomes 2 since we are estimating in this 2. So this is now 0. So this becomes 2. So we take 1 here. It's remaining 1. So it becomes 2 here. So we take 1 that's remaining 1. It becomes 2. 2 minus 1 is 1. 1 minus 1 is 0. 1 minus 0 is 1. So the same thing happens here. We borrow 1 here, so it becomes 0, it becomes 2. So we borrow 1 again, then it becomes 2. We borrow 1 here, it becomes 2. So 2 minus 1 is 1. 1 minus 1, 0, 1, 2. So here we have the BCD, right? So we now have to convert the BCD to decimal. So it means for the 8421, so it means 4 is turned on and 1 is turned on. 2 and 8 are turned off. So 4 plus 1 is 5, and this is 5. So that gives us decimal. So decimal is. So let's quickly look at the gray code. Now, the gray code is not a special type of BCD. So it is not a special type of BCD. So the algorithm for converting from binary code to gray code and from gray code to binary are quite different. So let us look at the algorithm for converting from binary So the first thing here is that the left bit is the same in the capital. It's the same in the gray as in the binary. So add the most significant bit to the bit on its immediate right. then record the sum. So in this case, we are going to neglect carry the gray code line. Third point is to continue adding bits, bits on the right, then recording sum onto the least significant bit is recorded. And the fourth point here is that the gray code number will always have the same number of bits as the binary number. So let's consider an example. So let's assume we have the binary number 0, 0, 1, 0. Okay. Then we want to get the gray code, right? So here we retain the first digit here, which is 0, and then move this from this position to this position. You get 0. So 0 plus 0. So we're going to get the sum. It's still the same as 0. So we move these bits this way. 0, 0 plus 1. So we're going to get the sum. 0 plus 1 is 1, right? Then we move this 1 to this position. 1 plus 0. So we get the sum. 1 plus 0 is 1. So that is the gray code. So what if we have 1, 0, 1, 1, 0? This is binary. And we need to get the gray. Right? So we retain the first digit here. That's what we have here. The left bit is the same in the gray code as in the binary. So this is the same. So we move this way. So 1 plus 0. So we get the sum. 1 plus 0 is 1. So we move the 0 here. Right. 0 plus 1. So the sum is 1. So we move the 1 here. 1 plus 1 is 2. 2 divided by 2 is 2. Then it means that we have 2. We have 2 divided by 2, which is 1 remainder 0. So we are going to document the remainder here, which is 0, and then we carry the 1. We drop the 1. And then 1 moves here, 1 plus 0 is a sum. Now, still on gray code conversion, gray code, let us look at the algorithm for converting gray code to binary. So the first point here is that the left bit is the same the binary number as in the gray code, right? The second point is that the significant bit of binary number is transferred to the top of the second most significant bit of the grid code. Then at the top point here, so repeat until for all other bits, bit sequence, adding the bits while collecting any card. Then the fourth point here is that the binary number always have the same number of bits. So let us convert the grid code. Say we have this grid code 1001 to binary. So here we retain the first bit here, and then remove this. This, and add them together. Then what do we have? 1 plus 0 is 1. And then remove this again. And we add sign 1 plus 0 is also 1. Then this again, which is 1. Then we add. So 1 plus 1 is going to give us 2. 2 divided by 2 is 1, remainder 0. So document the 0, neglect 1. Right? And go with them. Then let us look at another example. Say we have 0, 1, 1, 0, 1. So this is great. Great code. We want to achieve the binary code. We already know that we return the first leg bit here, that is same as 0. So move this way, as 0. So sum 0 plus 1 is 1. So we move this again to this. So we add it together. 1 plus 1 is 2, 2 divided by 0. So we neglect the carry. So move this 0. Sum is 0 plus 0 is 0. And move this again, that is 0. 0 plus 1 is 1. Move this here is 1. 1 plus 1 is 2. So sum is sum, right? So that would be 0. Then the carry, which is 1, we neglect. So this is equivalent of the group. So now that we have described that, let us look into logic gates. Coming back to our levels of abstraction. Logic gates. Now, logic gates are usually drawn with a symbol showing the input or outputs as a form of interrelationship based on the logical operation. Okay, so the relationship between the inputs and the outputs may be described with a Boolean equation or a truth table. So here we say that the truth table lists inputs on the left and corresponding output on the right. It has one rule for each possible combination of inputs. So on the Boolean equation, I have Boolean equation. It's a mathematical expression using binary variables, right? So let us look at a few types of logic gates. So we have a NOT gate. So here we have as the output, here we have the X as the input. So in this case, we have one input logic, right? So here, the output Y is the same as by X. This is the Boolean equation. And then for the truth table, we have X and Y. So we have two possible input combinations. So if we feed zero input, then we're going to get an inverted equation, which is 1 as the output, and if 1 is the input, then we have 0 as the output. And this is the truth table. So we also have a buffer. Which is usually described as buff gate. It's more like the NOT gate or the inverter. This is also called the inverter. Why the buff gate is more like the inverter, only that we do not have the circle at this point. So what we have as the input is what we get at the output. So Y is the same as X, is the Boolean equation. Y, X, Y. So given 0, we have 0, given 1. This is the truth table. So the buffer is more like a wire, right? Then we also have the AND gate, right? The AND gate. So usually we have 2 or more inputs. Something we have AB as an input and Y as an output. So Y is the same as A dot B. This is the Boolean equation. And the truth table, AB, Y. Since we have 2 inputs, 2 to the power of n is 2 to the power of 2, which is 4, right? So I'm going to have 4 possible combinations. of the input bits. So we have 0, 0, 1, 1, 0, 1, 0, 1, right? So 0.0, which is more like multiplication function. So that's 0, 0.1, 0, 0, 1.0 is 0, and 1.1 is 1. This is the truth table. Then we also have the OR gate. OR gate, which looks something like this. So input, AB, and the output 1. So this is more like addition. So Y is the same as A plus B. Is the following operation by the truth table. Since we have two possible inputs, so 2 to the power of n is to the power of 2, which is 4 possible input combinations. So 0, 0, 1, 1, 0, 1, 0, 1, right? So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. This is 1. This is the truth. Then we have the exclusive OR. Okay. 5. Exclusive OR, which is usually XOR. Okay. So usually this one. A. So here, A and B is separated upon using the movement of 2 addition, right? So A, B, that is the output 1. So for possible combinations, since we have 2 inputs, so 0, 1, 0. So for the exclusive OR, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0, and 1 plus 1 is 0. More like 2 divided by 2 is 1 remainder 0, so drop the 0 and this out. So this is the truth. Then we also have the NAND gates, which is the AND gate connected to an inverter, right? So conventionally, it is given as this is the circle here. So we have AB as the input and the output. So this is the same as Y, then the same as AB. Okay, this is the volume operation. All right, the truth table, AB, Y. Have 4 possible combinations, 0, 0, 1, 1, 0, 1, 0, 1. So if we have 0, 0 this way, 0.0 is 0 here, and at this point it's inverted this one. So this is, so if we have 1, okay, say 0, 1, this times this is still 0, 0 here, and this. The same again when this is 1, 0, that's 0. So when we have 1, 1 here, so we get 1, and once it's inverted, it's 0, right? This is the truth table. And also we have the NOR gate, which is the same as the OR, having an inverter output. So that gives us A, B. So here, Y is the same as A plus B bar. So A, B, Y. We have two inputs, so for possible input combination 0011, 010. So this plus this is 0, 0 comes here, and it's inverted as 1. 0, 0 plus 1 is 1 here, it's inverted is 0. 0 plus 1 is 1 here, and once inverted, so 1 plus 1 is 1, once then inverted here. This is the truth table, while this is the Boolean information. Now, it should be noted that gates are grouped into logic families, such that all gates in the logic family obeys the same static discipline when used with other gates in the family. So, what is static discipline? So, static discipline implies that when given logically valid inputs, every circuit element will produce logically valid outputs. So some of the major logic families transistor logic, just TTL. We have complementary, metal oxide, semiconductor. Logic. And then we also have the low voltage TTL logic, that's the LV TTL, and the low voltage CMOS logic, LV CMOS. Now, these logic families differ in the method they use in carrying out the logic and the coupling to the inverter stages. Now, it should be noted that the logic families are integrated circuits. So these are digital integrated circuits. And we already mentioned that the earliest logic gates utilized the TTL. And for some obvious characteristics that we are going to be identifying shortly, you will see that the reason some of the common digital designs make use of the complementary metal oxide semiconductor logic. So let us look at some of the characteristics of the TTL logic. So the first point here is fan in. Now this is the maximum number of inputs to the gate, right? So TTL NAND gates provides 1, 2, 4, or 8 inputs. That is TTL NAND gates from 1, 2, 4, or 8 inputs. And if more than 8 inputs are required, then the network of NAND gates must be employed. Then we have fan out. Now this specifies the number of standard loads that the output of a gate can drive without impairing its normal operation. So a standard load is defined as the amount of current required to drive an input of another gate in the same logic family. Okay, so let's put it there. So based on the nature of the TTL gates, two different fan-out values are given, okay? So one for high output and another for low output. Now, a typical TTL gate can source, let's change the color, can source 400 microampere input, output high, max current, and this can source and can sink 16 milliampere. So for the TTL gates, we typically have a high logic level funnel. Which is same as mod minus 400 microampere divided by 40, which is the same as 10. Okay? And a low fan out, this is high, so let's document it. So TTL. So exceeding these fan out limits may result in incorrect voltage levels, and they are, as a gate, cannot provide or sink enough current. The lower value of the two fan out values determines the fan out of the gate. And then we have the third characteristic for the TTL as the voltage transfer curve. Voltage transfer. Now, in the voltage transfer curve, we see a graph of the input voltage to a gate versus the output voltage. The input voltage to the output voltage. So when the input voltage V in is the same as 0 volts, the output voltage is high. V out is about 3.3. Okay, as you can see here. So as the input voltage is increased from 0 to 0.7 volts, the output voltage remains relatively constant. Okay, right? Region 1. Now beyond 0.7 volts to about 1.2 volts, the output increases more gradually with increasing input voltage in the region 2. Now the threshold voltage, which is at this point, of intersection, which is the voltage on the transfer curve at which V in is the same as V out, is found at the intersection of the transfer curve and the line V out equal to V in region 3, right? So finally, in region 4, the output remains constant at 0.2 volts. Okay, let's see, it's just 0.2 volts as the input voltage increases. Okay. So the next characteristic we want to mention here is noise immunity. And this is a measure of the ability of the digital circuit to adapt logic level changes on signal lines when noise causes voltage level changes. So one measure of the noise immunity is characterized by a pair of parameters. So we have DC high, which which is DC1, and DC low, which is DC0. Such that DC1 is the same as zero. Note that the minimum values of the DC high and the DC low determines the worst case noise immunity. So V0L max is the largest voltage or output. Okay. And the output is zero voltage range. Right? Right. V voltage means the smallest voltage that can occur in gate output. Output is high which means smallest input voltage that will be interpreted as a high voltage. Max greatest input voltage that will be interpreted as a low input. So here, you note that VOL and VOH are usually specified by the manufacturer on the data sheet for the devices, while VIL and VIH are usually determined from the voltage transfer curve given the VOL and VOH. So for TTL families, typically for TTL, DOC, DC 0, 0.8 minus 0.4, which is 0.4 volts, and DC1 2.4 minus 2.0, which is same as 0.4. So the next point we want to consider is the propagation delay time, another characteristic for the TTL. Now, this is the time required for the output of a gate to respond to a change in the input, okay? In all practical gates, a time lag exists between an input change and the corresponding output response. So the time interval between the instance when the input and the output changes states is not a satisfactory measure of the delay time of a logical device for two reasons. First, the input signal to the gate and then the output signal produced by gates are not the idealized courses studied in theory. Now, you will notice from this schematic, so from this schematic for the non-ideal input and output signal to a NAND gate, this NAND gate here, note that the transition between the high and the low voltage, level for voltage level here, have non-zero rise and fall times. Now, the rise time, let's say rise time, which is TR, is the time required for signal to rise from 10% to 90% of this final value. While the fall time, which is T sub F, say is the time required for signal to fall from 90% to 10% of its initial. So, and the second point is that the input voltage to a gate has only to reach the threshold value or level before the device begins to change state. For these reasons, the delay time is measured with respect to reference voltage level, or the threshold voltage. So if we observe the figure shown for the NAND gate, you'll observe that the NAND gate in this system is connected as a NOT gate. Yeah, looking at it, logically. So the input waveform Vn in this case is a non-ideal pulse. Now, when the input signal goes high, the output will go low. This is the output. So as this is going high, the output is going low. After the turn on delay time, is the turn on delay time, here CPHL, the turn time. Now, a typical turn on delay for a standard series TTL NAND gate is about 7 nanoseconds. Now, when the input signal goes low, again, the output of the NAND gate is sent to go high after the turn off delay time. That's TPLH, which is the turn off time. And for TTL, the typical value is usually 11 nanoseconds. So the average propagation delay, time, T sub P, is therefore given as T plus TPH, that is the average value between the turn on delay time and the turn off delay time. And then the maximum value of both the turn on delay time and the turn off delay time is usually 15 milliseconds, right? That is. Now, in the case of CMOS logic family, they are characterized by extreme low power consumption and high noise immunity. That is why they are preferred. Okay? So, having done this, but for the CMOS, they are characterized by not just low, extreme, okay? Extreme low power consumption and high noise immunity. So unlike the TTL logic, CMOS logic requires to supply voltages, okay? So we have VDD. Now in typical logic design, the VDD ranges from positive 3 volts to about 16 to about positive 16 volts. Yes. Why the V sub SS is usually grounded, right? So if we consider the logic level of 5 volts and 3.3 volts logic family, so we have logic family. TTL, 75 to 5.25, 0.8, 4, CMOS, 5, 5 to 6, 35. So I have low voltage TTL, just 3.3. 3, 6, 8, 0, and we have CMOS, 3, 6, 6. So one more thing we have to look into now is the transistor equivalent logic gates. Two types of transistors to be considered for logic gate design are the N-type MOSFET and the P-type MOSFET. So we have N-type MOSFET and the P-type MOSFET, right? So this could be referred to as InFET, right? This is referred to as InFET. Whether still could also be referred to as NMOS, right? This as CMOS, right? And whichever way, for the N-type to be represented in this manner where this is the gate. So, and here we have two logic levels. For zero logic, we have an open circuit, and for one logic, we have a short circuit. Right, for the P-type, to be represented as this is the gate. So we have circuit somewhere here. So in this case, the zero logic is a short circuit. Logic is an open circuit. So here you note that the NFET passes a signal when the input is 1. While PFET passes a signal when the input is 0. So NFET are like switches, okay, that are closed when the gate is fed with an input of 1 and are open when the gate is fed with an input of 0. So NFET are like switches. And the PFET are like switches also that are closed when the gate is given a 0 input and are open when the gate is given a 1 input. So a logic gate can be designed by combining the NFET and the PFET. So let us look up some of the logic gate designs. So we have the NOT gate, or that we have X, Y. This is the inverter actually. Inverter. X, Y, 0, 1. So here we can combine P-type and the N-type. And this is the drain is connected to ground. So this is the output. Y. Right. Have the gates connected to the. So here we have the source connected to ground, and the drain is fed the voltage supply, then the gate is fed in. So in this gate, in this case, this is a CMOS inverter, right? So the NOT gate is designed using two transistors, okay? So if X is fed with an input of 1, for instance, then the PFET is turned off, okay? So this operates as an open circuit. So when X is equal to 1, so what do we get? So it means that and the PFET acts as an open circuit, right? So it means that VDD does not get into the circuit, so it's open, right? And then what we now have here is no voltage here is 0 volts, right? And then this is grounded to the reference voltage here is 0 volts, right? So what is seen at the output is 0 volts when X is equal to 1. So when it is equal to 0, the P-type is a short circuit. So what we now have X is equal to 0, so that comes in here. So the P-type operates as a short circuit, so we have VDD, right? Why this operates as an open circuit, right? So this open. So at the end of the day, what we have is just a Y because this is open. Yeah. So this is 0 voltage. So the high voltage here is what you see. So this is 0, then what is seen here is 1, right? Because it is connected to the voltage source, which is 9. So if S is 0, the PFET is on. This is on. So the voltage value is seen here. And then the NFET is off, so 0 voltage is seen here. So let's see the AND gates. In this case, in time. So, N time. This is grounded, which is the same as a reference voltage of 0 volts. So in this case, the gate requires 6 transistors, 1, 2, 3, 4, 5, 6. So 3 p-type and 3 n-type. Okay. So when we have 0 input here and 0 input here, this is short circuit, right? As a short circuit. And then this acts as an open circuit. So the voltage here is short circuit, and then this acts as an open circuit, so a 0 voltage comes in here, and then as a 0 voltage comes in here, this now operates as a short circuit, and then this as an open circuit. Okay, so this is grounded, and then the consequent effect gives us an output of 0. So when this is 0, this acts as a short circuit, and this is a short circuit. So 1 appears at this point. So 1 at this gate becomes an open circuit. So we have 0 appearing here. And since this is 0, this is open circuit. So 0, 2 is appearing here. So the output is 0. Okay. So when this is 0, this is a short circuit, this is an open circuit. So, and this is a short circuit, this is an open circuit. So since this is open, now a 0 appears here, but now this is a 0, is short, and this is open. So at the end of the day, 1 appears here, and then we have 0. Okay? And now this is 0, this is open here, so what is driving this gate is equal to 0, so the output is 0. The same when this is 1, and this is 0, right? And this is 0, this is 1. So when this is 1, and this is 0, this is short, this is open, so 1 appears here, then this becomes an open circuit, and this is 0. And now this is 1, but this is open, 0. So 0 appears at this point, and then 0. So when this is 1, and this is 1, this is open, so 0 appears here, right? As 0 appears here, then this becomes 1. And now this is equally 1, 1, so this is short. So, and then 0 appears here, so that is 1, and then 0 appears here, this is open, so the output we see here will be equal to 1. Okay. So now let us look at the NAND gate. So, right? So we have two peptide together. By the voltage, then the N type. Okay. So when the input here is 0, the P type acts as a short circuit, So what appears here is 1. And this is open circuit. So what we get here is 1 plus this is 0, 0. Now when this is 0, 1, this is open, and then this is short. So the voltage appears here. So this is 1. And then this is 0, this is 1. So nothing appears here. So when A is 1, this is short circuit. When A is 1, yeah, the P type acts as an open circuit. And then B is 0, this operates as a short circuit, so the entire voltage appears here, so the output again is 1. And then this is 1, short circuit, this is 0. Okay, so don't forget this is grounded, GND, so B right here is equal to 0. So when this is 1, 1, now for the P type, it acts as an open circuit. So this voltage doesn't drop here because the point voltage here is disconnected, so it's 0. Voltage appearing here because this is 1, and this is seen as an open circuit. Yeah, it's an open circuit when A and B are 1, and this is short. So this is more like a short circuit here. This is a short circuit here. So the voltage at ground potential is seen here 0 volts, and this is also open voltage because for the P type, this is seen as an open circuit. So this is also seen as a 0 volt. So output is 0 volts. Then we equally have the OR gate. From A, B, I, 0, 0, 1, 2, 0, 1, 1. Right? So, right? Right. So we have P type. So we have the gate, the source, and the drain. Okay, so now for the OR gate, so for 0 input, this is seen as a short circuit. So for the voltage level is same here, this is 1, and then since 1 is appearing here, then this operates as an open circuit. So what we get here is 0, right? Let's see here is 0. And then this is 0, 0 is all zeros here. So what is also is open circuit. So what is in here is 0. So yeah. When it's 0, 1, so this is short circuit and open circuit. So the link is broken here. So what is in here is a 0. And then since it's a 0, it's now a short circuit. And then this voltage value applied. So it's now 1, right? And then this is 0, 1. This is short. So it's 0 voltage there, right? So 0 voltage appears here, but 1 appears here. So that is there. So the same when this is 1 and this is 0. So it's broken here, so it's 0 appearing here. So what drives here is now the 1, and then what is appearing here is equally 1. So 0, 1, then trigger here is 0. So now when you use 1, 1, so this is broken, this is open circuit, so 0, then what appears as 1, so that's that triggers, so this is short circuit, and then this voltage value is same here. And this also the voltage level here is 0, so what you see is. And then for the NOR gate, that 0, 0, 1, 1, 0, 1, 0, 0, 0. So we have P type, K1, and the voltage level. Grounded, 0 volts, mental, A. So when this is all zeros, the input also all zeros, so this operates as a short circuit. So the voltage level is same here, so the output here is 1. And this is grounded, so open circuit. So when this is 0, 1, then this link is broken. So what you see here is 0. And then 0, 1, so what is grounded is 0. So 1, 0 also, the link is broken. So what is in here is 0. So when both are 1s, so this is broken. So this voltage level is at this point it is seen as a short circuit, also as a short circuit. So here is 0. So this link is broken, and here it is connected to ground. So the potential voltage difference here is 0. The node voltage here is 0 volts relative to the ground potential. So 0 volts, and then the output voltage is 0. So we only have the exclusive OR gate. Now for the exclusive OR gate, A, B, A, 1, 0, 0, 1, 1, 0, 1, 0. Then we have 0, 1, 1, 0, right? Then we know that the exclusive OR gate can be designed using two AND gates, two inverters, and a single OR gate. All right. That's it. One focus. So, so this is A. So this point, so in other words, with an inverter, with two inverters, and two AND gates and one OR gate, then we could design the exclusive OR gate. And then this follows directly from, so here we have the NOT gate, yes. We have the AND gate, we have another AND gate, and then we have the OR gate. So all we need to do is to interconnect them. Okay. Now we have that. Let's use something else for the connection points. So in this case, by this. And then this. And then this. Swing. This. This. And this. So we are almost done. Okay. So it's connected already. So on this, also this, 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 and this now. Output. one not gate. There's another not gate. This is one gate. This is another gate. And this. So for the exclusive OR, for instance, for the exclusive NOR gate, we have this with an inverter connected A, B, and 1, such that A, B, Y, 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, right? So in this case, the design is similar to this, only that at this point, we now have enough gates to make it XOR. So having gotten this design, all we now need to do for the SNOR, for instance, is to interface with the NOT gate, right? So all we need to do now is to include the NOT gate there. This we do here, and then this we do as well. So this is not excellent, right? So, so it should be noted. It should be noted that the